All right, let's look at section 3.4, exercise 6. So we have a rectangular box. Looks like it's fully enclosed. So first I'm going to draw a picture, and this is not meant to do anything other than help me organize my work later. So I have a rectangular box, and what is important about it? The material for the sides cost $1.50 per square foot, and the material for the top and bottom costs $3 per square foot. If you're willing to spend $15 on the box, what's the largest volume it can contain? So what's the first thing we should do? So we're looking at some context and we want to optimize something. So first thing I want to encourage you to do is to um, figure out what your objective is. So in this case, what's our objective and what are the things to look for in the wording of the question to help you determine that? So I'm going to start looking for superlatives. So in this case, I have largest volume. So that's a good indicator to me that my objective function will have something to do with the volume of this box. And in this case, that's going to be, so this is the volume of a rectangular box, but I know something about it. It's not just any rectangle, it's going to have a square bottom. So for right now, I'll say the volume is equal to length times width times height. So that's three variables, which is something I really don't want to deal with, but maybe we don't have to. So let's keep looking. It has to have a square bottom, so I'll do this. I think I can say that both this dimension and this dimension are x. Because if the bottom has to be square, then I don't really have three different dimensions, length, width, and height that I have to worry about. I just have two. So the bottom has to be square. The third dimension does not have to be the same value, so I'm going to call that height. So I'm going to rewrite this volume as a function of, let's just rewrite the whole thing. So this is the volume of both x and h. So the volume is equal to x squared h. I'd rather not deal with that though, because that's two variables, two independent variables, and I really want to get this thing down to one. So how can I do that? So the objective function is one thing that's going to help me do this, but if I wanted to maximize the volume, I would just make the box as big as I could, like bigger and bigger and bigger. But I can't do that. I have a constraint. So next thing I want to worry about is what that constraint is. So is there some kind of requirement that I have to fulfill? Typically in a real situation like this, you have to model like you are going to be constrained by resources, time, material, money, hours, that's something. So in this case, what am I constrained by? So I am willing to spend $15 on the box. So my constraint is going to be a function of cost. Probably also going to be in terms of X and H. So how am I determining how much this box costs to make? That's going to come from a surface area calculation. So the material for the sides costs $1.50 per square foot. The material for the top and bottom costs $3 per square foot. So what I really have is a surface area calculation. So instead of first writing this as a cost, let's write this as a, actually, let's do it in one step. How do I find the surface area of this thing? So this is a box, a rectangular prism, so it's going to have 6 faces. 4 of those faces are the sides, and they are going to cost $1.50 to make. So the area of this face here, like on the side, this is HX. This one's HX. The two opposite them are both HX. So I'm going to have 4 sides whose area are HX, and they're each going to cost how much? They're each going to cost $1.5. I'm also going to have two sides, the top and bottom, which are going to be x squared. So 2x squared, and how much are those going to cost? Those are going to cost $3 each. So if I clean this constraint equation up a little bit, I get 6hx plus 6x squared. And that total, I want to spend $15. I'm going to spend the full $15 because I want to make it as big as possible so I can get the largest possible area. So now what I want to do, I want to take my objective and constraint and combine them in such a way that I only have one variable. So what I'm going to do with this constraint equation is solve it for a single variable. I think the variable that would be easiest to solve for in this case would be h. So let's go ahead and work towards that. So 6hx equals 15 minus 6x squared. So h equals 15 minus 6x squared over 6x. Can I simplify it all? 15 over 6, that reduces to 5 halves. Yeah. So 5 over 2x and 6x squared over 6x, that reduces to x. So my height is equal to 5 over 2x minus x. Now what can I do with that? Now I can combine those. Now I can say my volume is a function of x, and that'll be equal to x squared times h, but what is h? H is now 5 over 2x minus x. And if I do some simplifying, I get 5 over 2x minus x cubed. So now I have a function, an objective function that's in terms of only of a single variable. So now I want to find a maximum. I have a differentiable function. So my maximum will likely come from the first derivative. So v prime of x equals what? 5 halves minus 3x squared. I'm going to set that equal to 0 and solve. So I get 3x squared equals 5 halves. Or x squared equals 5 over 6. So x equals the square root of 5/6. Let's get an approximation for that number. So I'm getting a dimension for x of about 0.913, what we say, the feet. All right, are we done though? Let's look at what the question was. What is the largest volume it can contain? So I think we found the independent variable, or the value of x, that will give us the highest volume, but now let's actually find what that is. So what is the volume of 0.913, or when x equals 0.913? That's equal to 5 halves of 0.913 minus 0.913 cubed. Let's get an approximation for that. And I get a volume of approximately 1.52. And what should the units be? They should be cubic feet. Okay. So how do we feel about that answer? One more thing I will do for this question. I don't know if I'll do it for the other three that are due for this module, but I'll do it at least once here. I want to make sure that's actually a maximum. So I now have a critical point. Let's use the second derivative test to make sure I'm right. So v double prime of x is equal to what? Well, the first derivative is 5 halves minus 3x squared. Second derivative will be negative 6x. So if my derivative is negative 6x, my value of x was positive. 0.913 feet, then this is going to come out to be negative. So if I have a negative second derivative at a critical point, that is going to give me a local maximum. So I feel even better about this answer now.